All right, this is chapter 9, where we're going to start talking about the more specifics of chemical bonding. Okay, and we're really going to focus in on the Lewis model of bonding here, and then we'll expand that in the next chapter. Because we have 3 bonding theories that we have to focus on to understand, to get our best understanding of how different atoms are going to bond. We have to know why some combinations of atoms are stable and others are not stable. We can use bonding theories to predict the shapes of molecules. And we've already seen how we can use some of these properties or some of these theories to predict different chemical and physical properties of compounds. And the simplest bonding theory is called Lewis theory. That's going to really focus in on valence electrons in order to explain bonding. When we actually start looking at the individual atoms that make up the compounds that we're looking at, we're going to start drawing what are called electron dot structures or Lewis structures. Okay, and you've seen those. Those are the ones where you have the atoms. They're connected by lines, which represent bonds. And then they have the dots around them that represent the non-bonding pairs of electrons. And Lewis structures are going to help us predict a lot of properties of molecules. They're going to help us predict the stability of them, the shape of them, the size of the molecules, and the polarity of them, whether something is polar or not polar. When we have to think about why atoms are going to bond with one another, our main focal point is this right here: lowering potential energy. Okay, atoms are only going to come together and form bonds if it lowers the potential energy. Okay, a chemical bond is going to form when the potential energy of the bonded atoms is less than the potential energy of the separate atoms. That's how this stuff happens. And these are the interactions that we need to specifically hone in on when we're considering whether potential energy is lowered or not. We have nucleus to nucleus repulsions between positive charges. We have electron to electron repulsions between negative charges. Then we also have nucleus to electron attractions between opposite charges. Okay, and these are the 3 types of bonds that we are going to look at. We have our classic ionic bonds, which are metal and nonmetals bonding together. There is a transfer of electrons that happens. Our non-metal bonding is covalent bonding, and that is a sharing of electrons. We also have a new type of bond that we're going to look at now. It's called metallic bonding. And that's when we have different metals that are bound together by a pooling of electrons. And we'll look at that a little more detailed in a few minutes. So ionic bonds, I feel like we've covered this in pretty good detail so far. What makes an ionic compound, what would cause an ionic bond. Our metal atom obviously is going to lose its electron and become positively charged. This happens because metals have a low ionization energy, which makes it relatively easy to remove electrons from them. Our nonmetal, on the other hand, is going to gain an electron and become negatively charged. And this has to do with nonmetals having high electron affinities, right? So it makes it advantageous for them to add on electrons to those atoms. Then that oppositely charged ionic situation is going to lead to attraction between the 2 ions that will result in an ionic bond. Okay, and there's a little visualization there for you. I skip over my When you have your nonmetals bound together, this is going to be a little bit different because we don't have a situation where we have, you know, one atom that wants to give up its electrons and another atom wanting to pick up electrons. Here you have nonmetals. Nonmetals in general are going to have higher electron affinities and higher ionization energies. So they're not going to want to, you know, they don't do opposite things. Like metals and nonmetals, they do opposite things with their electrons. So transferring electrons from one to the other makes sense. With nonmetals, you know, everything kind of has a high ionization energy, so nothing wants to remove electrons. So instead what happens is they decide that it is more energy efficient to share electrons between them. Okay, and it turns out that the potential energy is lowest between nonmetals when the electrons are in between the nuclei of different atoms. That's kind of what this is visualizing down here. You know, you have low energy, the lowest energy situation where you have your electron or your negative charge that's just kind of dead between two positively charged nuclei. Okay, because you see you would still end up with some repulsion here. You would end up with some repulsion here. But with this negative charge in between the two positive charges, that would limit the amount of repulsion that happens between them. And the third type of bonding is the metallic bonding. And this is kind of the most new one that we're going to look at, the weirdest one. If you look at these pictures, you can imagine that the solid purple in the middle, that's representing whatever the metal is that you're looking at. The one that's depicted here is sodium, but it can be any metal. And those solid colors are the positive cations of the metal after they've released their electrons. And these sort of translucent blue spheres around them, that represents the electron sea that exists surrounding the metals in general. Okay, it's very easy for metals to lose their electrons because of their low ionization energies. So what ends up happening is that the metal atoms are next to one another, and because of their low ionization energies, they lose their electrons. The electrons then kind of organize themselves around an island of metal cations. Okay, so you can think of the metal cations as the island, and there's like a sea of electrons that's surrounding the island. And the electrons are delocalized throughout the metal structure that way. All right, what does delocalized mean? It means that they're detached and they're not in one particular location. All right, so our electrons are actually able to move around in this sea of electrons, and that movement of the electrons explains a lot of the properties of the metals. It explains why metals are conductive, right? Because you can't conduct electricity if you have no ion movement. But because the electrons are moving through this sea, this pooled sea, now they're able to conduct a charge. They're also malleable and ductile for the same reason. This pooled distribution of electrons is what gives metals most of their properties. We've already, I keep on saying that, we talk about the same things like over and over again because we're building foundations, obviously, but I just finished the chapter 8 lecture about valence electrons, so I really feel like I'm being repetitive here. Valence electrons are our outermost electrons, so they're going to be held most loosely by the atom. So all of our chemical bonding is going to involve transferring those electrons or sharing them. Okay, Because of these facts, valence electrons are the most important electrons in bonding, and Lewis' theory is going to focus heavily on the bonding, on the behavior of valence electrons in the bonding, rather. Okay, so we need to figure out how to count the number of valence electrons in an atom. We've already started doing that. The column number of the periodic table is going to tell us how many valence electrons a main group has. And when we have a Lewis structure, we're going to represent the valence electrons of main group elements as dots that are surrounding the symbol for that element. That will be the electron dot structure of an element or an atom. And we're going to use the symbol of the element. So this is the chemical symbol for oxygen. So we're going to use the symbol of the element to represent the inner electrons. And then we're going to use these dots to represent the valence electrons. So we can look at the electron configuration of oxygen, and we know how many core electrons it has and how many valence electrons it has. We're going to represent all the core electrons just by writing the letter O. And then we'll surround that O with the 6 dots that will represent the valence electrons of oxygen. When we're talking about Lewis bonding, it's not a surprise that when we're talking about what stable electron configurations are or stable structures are, we're talking about structures that have a lower potential energy than anything else. And atoms are either going to bind together by transferring electrons in an ionic bond or sharing electrons with covalent bonds, right? So when that happens, what we are going to see is all of our atoms in their outer shells, all of our atoms rather, that we're using to build our structure will have an outer shell that has 8 electrons in it, okay? And this is called the octet rule, and the octet rule governs bonding. There are obviously some exceptions to the octet rule, but 95% of the time, we're looking for an octet of electrons in the outer shell of any atom that we're using to build our compounds with, right? This makes sense because noble gases have 8 electrons in their outer shell. Everything is trying to be like a noble gas. Before I move on to that next slide, I just wanted to say one more thing. I'm probably having another slide later on, but one main exception to this is hydrogen, which is so small that it only wants to form a duet. So a hydrogen only needs 2 electrons to fill its outer shell because of its size. But other than that, we're looking for 8, all right? So here we go now. We're looking at potassium here. We have the electron configuration for potassium. It ends with 4s1. So if it loses its last electron and has 0 in its 4s, now its previous principal energy level has 8 electrons in it, and it is quite happy, right? Ionic bonding happens by transferring that electron, okay? So we see that this 1 dot right here, that's representing potassium's 4s1 electron, right? And we see that chlorine over here is missing 1 electron. So if potassium can get rid of its electron and that electron can go hang out by the chlorine, now both of these components have an outer shell with 8 electrons in them. All right? We can actually represent the transfer of electrons from metal atoms to non-metal atoms. Okay, and we can represent that bond. Now, when we're drawing ionic compounds, notice that we're not drawing a line between them. And that's because a line between them would represent electrons that are being shared. That's not what's happening here. We're transferring electrons and we're ending up with a cation and an anion. Okay, and you can imagine that they're bound together by charges instead. We are going to be able to predict the formula of different ionic compounds using this method. Okay, because a metal atom should lose electrons to gain an octet. A non-metal atom should gain however many electrons it needs to make an octet. And sometimes, you need to pick up electrons from more than one metal, or you need to distribute your electrons to more than one non-metal if you have more than one valence here, right? In this case, potassium had one valence electron too many, and chlorine had room for exactly one. So one potassium was able to give an electron to one chlorine to make this KCl ionic compound. But for example, if we were looking at something like calcium and chlorine, and we wanted to use Lewis symbols to predict the formula of them, well, when we write out the electron dot structure for calcium, we see that there are 2 electrons in its valence, right? And chlorine only has room for 1. Well, what is a compound to do? Well, the calcium is going to be like, oh, hey, bring a friend, okay? That's what's going to happen. So chlorine number 1 will come over and it will pick up this electron, okay? And then a second chlorine will come over and it will pick up this electron. So our ionic compound that's formed between calcium and chlorine will be a Ca2 plus ion and then 2 chlorine ions. Notice that when you have an electron dot structure that contains an ion, that there are brackets around the structure itself, and the charge is put on the outside of the brackets. All right, now the third step in figuring out the formula is actually writing the formula down. The formula is CaCl2. Right? When ionic compounds are formed, they form a crystal lattice, right? Remember, they don't form separate molecules, they form a crystal lattice where you have cations and anions surrounding each other, and they are held together by electrostatic forces. So a crystal lattice is able to maximize the attractions between the cations and the anions, which leads to a very, very stable arrangement between them. This electrostatic attraction, it's non-directional, so it's not pulling it in one direction or the other. There's no specific anion-cation pair. There is no ionic molecule, right? We only have our base formula unit. The chemical formula for any ionic compound is always going to be an empirical formula, which just gives the ratio of ions based on the charge balance, right? There is no NaCl molecule. It just happens that sodium and chlorine react in a 1-to-1 ratio. So we call our sodium formula NaCl, indicating that there's one of each. Now, this little guy over here, this is the next thing we're going to look at, the lattice energy. Okay, the lattice energy is the actual energy that's released when solid crystal forms from our separate ions. Okay, so when our positive and negative charges actually come together to form these ionic bonds and to form our crystal lattice, there is going to be a release of energy. Lattice energy is always exothermic because this process always releases energy. And lattice energy is going to be dependent on a few things, like the size of the charges and the actual ionic radius. It's real hard to measure lattice energy directly. We can usually get an idea of lattice energy based on other processes that we can observe. Let's look back at Coulomb's law for a second, just so that we can remind ourselves how we're going to measure energy. This is actually a better breakdown of Coulomb's law than what was in the previous chapter, mostly because we're actually talking about what your constant here is. But we have the charges of the two particles. We have the separation of the two particles, distance that you do want to measure in meters. And then we have our potential energy. And remember that it's positive for particles with the same sign in front of the charges, and it's going to be a negative potential energy for particles with opposite signs, right? Because we're talking about multiplying signs up here in the Q's. So the strength of the interaction is going to increase as the size of the charge increases. When these numbers get bigger, the strength of the interaction gets bigger. All right, now we can use something like what's called the Born-Haber cycle to figure out what the lattice energy of the formation of ionic compound is. But to do this, we have to have a lot of values at our disposal. Okay, we need to know each of the individual steps except for the actual lattice energy, and we need to know the heat of formation, or the enthalpy of formation, whichever way you want to say it, for the ionic compound that we're looking at. So this would be an example of how you would use the Born-Haber cycle to figure out the lattice energy of an ionic compound, something like NaCl. Each of these steps 1 to step 4, it's showing you the, it's like how each of the atoms kind of preps in order to get to this last step when the crystal lattice forms. So the first thing that happens is solid sodium has to be converted into gaseous sodium, and that costs a little bit of energy. Then chlorine gas, which is diatomic in nature, would have to separate into chlorine gas, and that's going to cost some energy. Then we're going to have the ionization steps. So gaseous sodium now has to turn into a sodium ion, and chlorine gas monoatomic has to turn into a chloride ion. Once these two components are in ion form, now they can join together and form solid sodium chloride. Okay, and that lattice energy is something that we can determine based on the heat of formation of sodium chloride, which we can get from those standard heats of formation values that we looked at in chapter 6. And then we're going to take into consideration our steps 1 through 4. Okay, so each of those steps, and then we can solve for our lattice energy. So the heat of formation of sodium is going to be the sum of steps 1 through 5. I actually have it written up here a little more, I think in words it might be better here. So the heat of formation, which is this value down here, which is a value that we're given in this case, that's equal to steps 1 plus 2 plus 3 plus 4 plus step 5, which is the lattice energy. So if we take this equation and we solve it for lattice energy, then it turns out that it's the heat of formation minus steps 1 through 4. Okay, so if we add steps 1 through 4 together and we subtract it from the heat of formation, what we're left with is the lattice energy, which is the energy that's released when that ionic compound is formed. Okay. You should know the steps of the Born-Haber cycle, but I don't think it's worth like breaking down different ionic compounds and solving for each step. But if you're presented with all of the data, if you're presented with the data from steps 1 through 4 plus the heat of formation, you should be able to solve for the lattice energy with all of that information. All right. You should also know the sort of trends that are involved when we're talking about lattice energy. So one of the big ones is that when you have a larger ionic radius, you're going to have a smaller lattice energy. And when you have an increasing charge, you're going to have a bigger lattice energy. And if you look back to your that formula that we were looking at before, that actually makes a lot of sense, right? Because if you look what happens, you know, if you increase your numerator, you get a bigger value. If you make your denominator smaller, you get a bigger value. So the force of the attraction between the oppositely charged particles it's going to be directly proportional to the product of the charges. So larger charges, that's going to mean that the ions are more strongly attracted to each other. And when you're comparing these two different factors, the charge factor and the size factor, the charge is going to always be the more important factor of the two. You know, so if you came down to having to make a decision based on the charges or based on the size, you're going to be like, all right, well, that charge is bigger, so that's going to have the stronger attraction. So why don't you take a second to try to order these, okay? Increasing lattice energy. So the smallest lattice energy to the biggest lattice energy. Okay, and think about why. What are we looking at here? We're looking at size and we're looking at charge. Okay. So these are our observed lattice energy values. Okay. And see how they get bigger as we go down. And the smaller charged ones have a smaller lattice energy than the larger charged ones. All right. So the next section that we're going to talk about is it's like models versus reality of the different of the bonding scenarios, okay? And it turns out that the Lewis theory of ionic bonding actually, it does account for a lot of what we see in nature, because, well, let's just go through and then you'll see. The first thing is that the theory implies that when you have very strong attractions between ions, it should be hard to separate them, right? Because when you have two things that are attracted to one another, like a positive and a negative pole, it takes a lot of effort to pull them apart. If that's true, then ionic compounds should have very high melting points and very high boiling points, because it should take a lot to break apart that crystal, to break the bonds that are between them. And this is what we see in nature. The melting points of ionic solids incredibly high, and they are all solid at room temperature. Lewis theory also predicts that ionic solids should be hard. Why is that? Well, if they're locked into position with their positive and their negative charges, you would imagine that it would take a lot of energy to move any of the ions out of position, right? That position in the crystal lattice is incredibly important to the stability of the structure. If you pull one ion out of the structure, the entire thing kind of falls apart. So when we say that ionic solids are relatively hard, that is it's actually like kind of a scientific term. We measure hardness by rubbing two materials together, okay? One of the materials will streak another one, or it will cut another one. So it will actually leave a mark, or it will indent on it. The harder material is the material that cuts, or it's the material that does not streak. All right, that material is the harder material. And ionic solids are harder than molecular solids, than almost all molecular solids. The Lewis bonding model also predicts that crystals will be unstable and break apart if that there needs like another part of that sentence where it says, you know, if you disrupt them or something like that. And that's true. Ionic compounds are brittle, which means that if you hit an ionic solid, that disruption in the crystalline structure will cause them to fall apart, right? They shatter when you hit them. And that goes back to what we were talking about over here with that crystalline structure being so important. It's like you move one piece out of the structure and all of a sudden there's nothing holding it together anymore. Okay, it just kind of all goes awry after that. You would also imagine that in an ionic solid, because everything is locked in place, all of your positive and negative charges are locked in place, that you wouldn't be able to conduct electricity through an ionic solid. And that is the case, right? To conduct electricity, a material has to have charged particles that can flow through the material. Ionic solids don't have that. They have charged particles that are locked into place, so they can't conduct electricity. If, however, you dissolve an ionic compound, or you have an ionic compound that's in its liquid state, then it can conduct electricity just fine, because now your charges aren't locked in position anymore. Now they're able to move around. Once the ions can move around, then they are able to conduct electricity. Okay, so that's the information for ionic bonding. Now we're going to talk about covalent bonding between nonmetals, right? Because our nonmetals are not going to be transferring electrons from one to the other. They're going to share electrons instead. And those shared electrons are going to be able to count towards both atoms' octets, right? So this is an example down here of a water molecule. Okay, so these electrons that are written in between the oxygen and the hydrogen, these are bonding pairs of electrons. They're going to be electrons that are shared by both atoms and that count towards the octet of both atoms. The oxygen has, in addition, 2 lone pairs. Those are electrons that only belong to the oxygen. They are not shared electrons, and they're only going to count towards oxygen's octet. When you have a single pair of electrons between 2 atoms, that's called a single covalent bond or a single bond. One atom can use more than one single bond to fill its octet, right? So oxygen here is using 2 single bonds, which is 4 electrons, plus its non-bonding pairs, which is also 4 electrons. That gives oxygen an octet. Hydrogen only needs a duet. This is, I guess, the slide where I mention it. So the one bond that hydrogen forms between itself and oxygen is enough to fill its requirement for its valence electrons. When you have 2 atoms that share 2 pairs of electrons, that results in a double bond or a double covalent bond. And each double bond equals 4 electrons, all right? Double bonds are shorter than single bonds, and double bonds are stronger than single bonds. And you can write it as either 4 dots between 2 atoms, or this is when it starts to get less messy to use lines to represent pairs of electrons. But notice that in both situations, each bond counts as 2 electrons towards each oxygen's octet. So oxygen 1 over here has 1, 2, 3, 4, 5, 6, 7, 8 electrons around it. Okay. The last type of covalent bond is a triple bond. Triple bond consists of 6 electrons, and triple bonds are going to be even shorter and stronger than double bonds. All right. It's very messy to draw triple bonds in terms of dots. It's a lot easier to draw it in terms of lines. So you see each line between this nitrogen will be 2 electrons. So 2, 4, 6 electrons here, plus the 2 from the lone pair here. Nitrogen has 8 electrons around it. So its octet is filled. Okay, so your Lewis theory is going to show the difference between stable structures and unstable structures. And you are going to notice that stable structures are going to be ones that combine to form the octets. All right? We're going to be able to predict the formulas of molecules of covalently bonded substances this way. Okay? We'll be able to figure out trends in different atoms. This is why, for example, hydrogen and other halogens are all diatomic molecular elements, because they have a stable structure that way. We'll also see why oxygen generally forms 2 single bonds or a double bond with other material in its most stable molecular compounds. Okay, here's an example of oxygen bonding in different ways. We have a stable oxygen over here in this H2O molecule, which we did previously look at. It has 2, 4, 6, 8 electrons around it. It has 2 bonds and it has 2 lone pairs. Okay, H2O is a stable compound. This next compound is H3O. Now notice, if we tried to form this compound, we would end up with an extra electron, because oxygen has 6 valence electrons and each hydrogen has 1 valence electron. So if we try to fit all the electrons that we have around the oxygen, we end up with 2, 4, 6, 7, 8, 9. Now oxygen has 9 electrons around it. That's more than an octet. Oxygen does not want that. Right? So what is a stable structure, though, is H3O+, which is an ion. Right? It's a hydronium ion that we looked at already. The hydronium ion looks a lot like this, except we're missing one of these electrons. So as soon as we're missing one of those electrons, now oxygen has 8 electrons again, and we find that this is a real and stable structure that oxygen can exist in. Another difference between ionic and covalent bonding is that the bonds between atoms and covalent bonds is directional bonding. Okay, when we talked about the ionic attractions, those were non-directional, right? They were happening in every direction. But covalent bonding is directional bonding. Okay, you're going to have, you know, there's a point A and a point B, and there's a bond between it. You know, this is the direction. It's not like in an ionic bond where you had, you know, if you focus in here on this particular anion, there are attractions 360 degrees around this particular ion. Hopefully that makes sense. Lewis theory also predicts that the melting and boiling points of molecular compounds is going to be low, as opposed to ionic compounds. And this is because of the difference between what happens when you are melting or boiling an ionic compound versus a molecular compound. The smallest unit of a molecular compound is a molecule. So when you are trying to melt or boil a molecular compound, you are just trying to separate the molecule into, or the entire compound into its individual molecules. You're not trying to actually pull these molecules apart. So these little dashed lines here, those represent intermolecular forces. Those are forces that exist between separate molecules of a molecular compound. When you are going to boil a molecular compound, you are trying to break these intermolecular forces apart, okay? But these intermolecular forces are not real bonds. They require much less energy to break than a real bond. So it takes less energy for you to, for example, if we're talking about water, if you were trying to separate two water molecules, they're not bound together with a real chemical bond. They're kind of loosely attached to one another based on the positive and negative charges of the polar water molecule. So it requires less energy to separate the water from one another and turn it into its gas form than it would to separate an ionic compound from itself. Lewis theory also predicts that the hardness and the brittleness of your molecular compounds is going to depend on the strength of the intermolecular forces. Okay, so a lot of what dictates how the molecular compounds behave is the strength of those intermolecular forces between them. And an intermolecular force is a force that happens between two molecules, not between the same, like not within the molecule. It's between two molecules. We don't have to worry too much about that now, that we're going to get into much more detail with that in chapter 11. Lewis theory predicts that molecular solids and liquids don't conduct electricity. That makes sense. There are no ions there. Molecular acids is an exception, but only when they're dissolved in water and ionized. Right? That's the same type of exception that we talked about previously. We can talk about the strength of ionic bonds, or not ionic bonds, of covalent bonds. Okay. We can determine the strength of a bond based on how much energy that we need to add to that bond in order to break it in half. Okay, so you'd imagine that the more electrons that two atoms are going to share, the stronger that the bond between them is going to be. So triple bonds are going to be stronger than a double bond, and a double bond is going to be stronger than a single bond, because we're sharing more electrons between two atoms in each case. We'd also should make sense then that the more electrons that two atoms share, the shorter that bond will be. And all of these things have the caveat that we're comparing bonds of similar atoms, okay? So imagine a whole bunch of like carbon-carbon bonds. We're not trying to compare like apples and oranges here. The more electrons are shared between them, the more the atoms are going to be pulled together. And when we measure bond length, we're looking at the distance between the nuclei of the bonded atoms. Okay, so triple bonds are stronger than double bonds, and they are also shorter than double bonds. Double bonds are stronger than single bonds, and they are also shorter than single bonds. So that's a good trend. That's an easy trend. We can also classify the type of covalent bond, maybe that's better. The type of covalent bond that we're looking at, based on how much, what type of sharing is happening, how much one atom is pulling on the electrons. You know, like there's different levels of sharing that happens, kind of like when you have siblings fighting over a toy. Some of them share really well, and some of them don't share well at all. We have a similar case here with molecular compounds and their covalent bonding. Bonds are classified as covalent bonds if there is not enough energy to transfer electrons, or the electronegativity is too small for an actual electron transfer to happen. So anything below a full electron transfer, which would be an ionic bond, anything below that level is considered a covalent bond. But now there's different levels of sharing that happens. You could have sharing that is 100% perfect sharing, completely equal. That type of sharing is a pure covalent bond. Okay? If you have unequal sharing though, and it's unequal sharing enough where you end up with dipoles within your molecule, that's called a polar covalent bond. So something like water, where you have a positive end and a negative end, that's a polar covalent bond, right? That unequal sharing. Here's another example. You have something like fluorine, which is highly electronegative. So it's going to pull all the electrons towards itself, okay? That creates a negative end, right? And it leaves the hydrogen over here with a slightly positive charge on it. But it's not a full transfer. This is still part of the same molecule. So you end up with a molecule. This is how you note a dipole that's within a compound. We'll get into what a dipole is in a minute. But in a compound like this, where you have charge separation, the positive charge is noted by this almost like a plus sign, and then the arrow end is towards the negative side. Okay, so when you note something like this, you're saying that it is a polar covalent bond. Hydrogen is your positive end, fluorine is your negative end. So this entire idea of having a polar covalent bond is based fully on electronegativity, okay, which is the ability of an atom to attract electrons to itself. And electronegativity increases across the period, and it decreases down a group. And if you think back towards our trends, that really does make sense. Our halogens are the most electronegative because they have room for that one electron, right? And the smaller the atom is, the more, the more that charge is going to affect it. So something really small and really electronegative like fluorine is going to pull very hard on electrons. The bigger the difference in electronegativity between two things, the more polar your bond is going to be. And the negative end is always going to be toward the more electronegative atom. All right? If you look back at your periodic table, or at least note it here so that you can go back and look, fluorine is your most electronegative atom, like I said, and francium is your least electronegative atom. And look at where francium is in your periodic table. It's toward the bottom and it's toward the left, right? So that basically, that trend is the opposite of atomic size trend. Right, so that's interesting, I think. It's maybe a good way to remember the electronegativity trends. And also you should note that noble gases are not assigned electronegativity values because they do not want anything to do with electrons. Okay, so francium here is the least electronegative out of everything. Fluorine is the most electronegative. So we're going from smallest to largest in that direction. This is the breakdown of the types of bonds. So if you have an electronegativity difference between two things of 0, that bond is called a pure covalent bond. If you have an electronegativity difference between two things that is between 0.1 and 0.4, that bond it's a nonpolar covalent bond. It's not a pure covalent bond because there's really small amounts of electronegativity difference going on, but it's still not a big enough difference for it to be considered polar. If you have an electronegativity difference between 0.4 and 1.9 though, Now we have a polar covalent bond. And any electronegativity difference that's greater than 2, that is considered 100% ionic. That is a full transfer of electrons. So we can measure the bond polarity by looking at the positive and negative charge in a molecule, okay, and seeing what that difference looks like. It's not the same thing as Coulomb's law, okay? I know that when you see charges and radius, that you look at and you'll be like, oh, I know that, but it's not the same thing as Coulomb's law, okay? You're going to literally just be looking at the charge difference and the actual distance between those two charges. And a dipole moment, which gets this weird little U symbol here, it's measured in what's called debis, okay, or a big D. Charge is measured in coulombs, distance is measured in meters, 1 debi is 1 coulomb meter, right? And the more electrons that two things are going to share, the larger the atoms are, the bigger the dipole moment is going to be, right? Because our dipole moment, U, is measured by Q times R. So if we have a big charge difference and we have a big radius, this dipole moment is going to get real big, okay? This is a list of some of the, and this is how your book has your electronegativity differences labeled. I also included the term pure covalent for you so that you would know what it meant when you read about it. But just take a look here at some of these. So look what happens here. You can actually like see when you have something like Cl2 and you have an electronegativity difference of 0, you have no dipole moment between them, right? When you have something like ClF, you have an electronegativity difference of 1. Well, that falls right into that polar covalent category. And your dipole moment between them is 0.88. Okay, it's not huge, right? Because they have very similar electronegativities. Our charges are identical. You have a size difference, but the charges are the same. Now you go to HF over here, 1.9 electronegativity difference, and your dipole moment gets even bigger. Lithium fluoride, an electronegativity difference of 3. That dipole moment gets huge. Okay, that distance between those two things must be very large. We can also tell the actual amount that the electron has transferred from one atom to the other by measuring what's called the percent ionic character. Okay, that's what this is over here. So a very high percent ionic character is going to mean that you have something that's getting much closer to what would be an ionic bond, right? 100% ionic character means you have an ionic bond. So as you approach a high percentage of ionic character, you're approaching that level of having an ionic bond. Okay, so why don't you take a minute and try these out. Hit the pause button, try these out, classify the bond that's formed between each of those pairs of atoms. Covalent bonds, polar covalent bonds, pure covalent, ionic. Okay. I'm gonna move on to the next one and show you what I got. So these are the electronegativity differences. Okay. Hopefully we all agree on these. Once you have the electronegativity differences noted, then you can assign bond types. So an electronegativity difference of 3, that's an ionic bond. 0 is pure covalent. 0.5 is polar covalent. I didn't have anything that fell into the non-polar covalent category, but you get the idea here. Okay, and that leads us up into drawing some Lewis structures, which we should take the time to do properly. It's very important for this, the rest of this chapter, and also the next chapter. I think I'll pause this video here and then just restart another one so that You can have like a Lewis structure video to look at.